as fluid enters the eye of the impeller here, and it will flow in these directions, passing the blades, and it will flow across the casing, and it will leave the pump eventually through the nozzle here. Now we can see that the cross sections inside the casing is increasing along the pathway into the nozzle. This circular path has a functions of as a collector. It can act as a collector and it can act as a diffuser. As a collector, it will collect the fluid and direct it towards the nozzle. And as diffuser, it will increase the static pressure of the fluid by reducing the kinetic energy. So as we know, as the cross section is increasing, the velocity will decrease as the Q is constant, and the velocity has to be smaller as the area is keep increasing up to the nozzle. And as we know that according to the configurations of the diffuser, a pump can be categorized first as veinless diffuser, and the second one, a centrifugal pump, can be named as vein diffuser. So in a vein diffuser configuration, there will be a static blade outside the impeller. So it will act as a diffuser with the shape of a static blade with some angle on it. You can try to Google it and find the images of a vein diffuser and has an idea how it looked like. Now let's discuss if a pump lies into the veinless diffuser category. So the veinless diffuser has a simple design and a simple geometry as depicted here on the left. It consists only of the impeller and the casing that increase the area up to the outlet or up to the nozzle. If we have a look on the side view of the impeller, so this is the nozzle if we look from the side view, and this is the front view, so to say, and these are this, and the pathway or the width of the impeller is V. We can write down the equations for the mass flow rate for the veinless diffuser, that is equal to density, area, and the radial velocity, or we can write it down as 2p multiply with radius of the impeller multiply with b, or the width of the impeller, and with CR, or we can write it down as CR equal to R2, or radius at the outer part of the impeller, multiply with B2, the width of the blade itself, density at the outlet, multiply with CR2, and divide it with the radius, width of the pathway, multiply with density. So this equations is actually from the continuity equations. And assuming that there is no frictions within the flow, we can estimate the tangential components of the absolute velocity, or Cx, multiply with R, that will be equal to Cx2 multiply with radius at point 2 or at the outlet of the impeller. And then from this we will get that Cx equal to Cx2 multiplied by R2 divided by the radius. And normally in a centrifugal pump, the absolute velocity has a close value to its tangential component, or to Cx, and then we can write down the equations as the absolute velocity equal to Cx2 multiplied by radius at the outlet divided by the radius.